read it. John Sleavin's engineering career includes an impressive array of transportation projects, including several in Malaysia, Singapore, and Portland. In Seattle, the projects he's been involved in are almost the history of major engineering projects within the region. They include Link Light Rail in Tacoma, the South Lake Union streetcar Sound commuter rail between Seattle and Tacoma, the original downtown Seattle Transit Tunnel, construction of the light rail segment from downtown to the airport, including Beacon Hill tunnels, the University and Northgate Link extensions, the 14-mile East Link extension, which includes the I-90 floating bridge. And now you oversee the link extensions to the Tacoma Dome, West Seattle, Ballard, and Everett, and operations and maintenance facilities north and south. Whew, that's a lot.
Wow.
You have an illustrious.
What are you doing? What are you doing the rest of your day?
Yeah.
Well, fortunately, it takes a village, and there's an amazing staff. So I get to get involved in all those projects. I hate to say I'm doing them all. I'm actually leading up the engineering side. There's project directors on those that are actually leading up those projects. But I'm doing a lot of consistency across those projects on the engineering. We try to get that involved early in the planning so that we're consistent on a lot of far-reaching projects.
So John,
the project
John,
that you're.
George, if I could hopefully deliver this next question with a smile on my face. I'm not from Seattle originally. I moved out here when I got married. And when I moved out here, there were 3 floating bridges in the state of Washington. And since that time, I've seen 2 of them go down. So I hope you're going to give me some confidence with this rail project across I-90.
I will tell you, all during the development of the design, almost every sentence ended with "and don't sink the bridge." That's high on everyone's mind. They're unique. The scale and the breadth that we have here on Hood Canal and Lake Washington. We've learned a lot over the years, and we've used a lot of that knowledge and some of those same individuals to help develop this system. So yes, I'll touch on some of that during the presentation. But
great.
Okay, well, I think let's go ahead. Thank you for taking the time. And so you got the presentation right. So
I think the shared link went down when Robin joined.
Oops. Okay. Let me try that again.
There we go.
So now it's running. Okay, I will go on mute and we'll see.
All right, so we'll kick off here. Welcome to the SAE Northwest December 7th, 2021 presentation. Today, my name is John Sleavin. I work at Sound Transit and have had the honor of being able to work on the light rail floating bridge and placing light rail onto the I-90's floating bridges. So that's what today's going to be about the challenges and the opportunities that we've looked at. Today's meeting, I'm going to go over a video of the track bridge and the movable design. We're also going to talk about post-tensioning that was added to that bridge, the engineering of weight and balance on the bridge, because the bridge is really a marine vessel that can't go into port. So keeping the weight and balance and trim on that is very important. And then a wind and wave analysis. These are just some of the many challenges about putting light rail on the floating bridge. So starting out with the track bridge. What is a track bridge? That's the bridge that bridges the rails from the fixed bridge to the mobile part of the bridge. If you're familiar with docks on a tidal place where the bridge goes, the dock would go up and down with the tides. The bridge does the same thing because the lake level changes. There's a transition slab between that movable part and the fixed part, much like a gangway between a boat and a dock. So we have to, at that each end of that gangway is a joint that cars kind of drive across. It's currently an accordion joint, but accordion joints don't work very well for a fixed rail system to go across it. So that was our challenge here. There's 6 points of movement at those 4 different interface points. Part of this development, we needed to define success, what we wanted, which was a comfortable ride at 55 miles an hour, which is our maximum operating speed. We also wanted to find what was acceptable going into this, so we knew what our parameters were. We thought if we had to slow down any farther below 35 miles an hour, we really needed a different system and need to go back to the drawing board. So that was kind of the parameters. Our goal was 55, definitely no less than 35 at that at those joints. And also we needed to know it, basically what's a failure? When is it time to start over? And again, starting that early on before we're even into this to define what we wanted, it's really helpful for us to check back up during the design process, that we didn't try to kid ourselves halfway through, like, yeah, that's good enough. We set those criteria early on. So the evaluation criteria that we were looking at, of course, was operating speed, speed restrictions that we might have from the wind and the wave or different environmental issues going on during different times of the year, reliability, maintainability, and inspection. Once you open a rail system, your riders expect a very high level of service and maintainability. So making sure that this track bridge system didn't require a lot of maintenance, didn't have to go out of service and interrupt that connection between downtown Seattle, Bellevue, and out to Redmond, which is a lot where the high-tech industries are located. Of course, ease of fabrication, initial costs are important, long-term operating cost, and again, as we talked about, customer impact. That's the last point, but really it's the bottom line, and that is the customer. We have to be thinking about that all the time because that's what we're building it for. And our customers are those people who depend on this service daily. So what did we come up with? We came up with what we called caesura, which is a curved element. And I'll play a little video on this, on what we're looking at here. So essentially, what we have are 2 curved elements that each rail sit on. Those 2 elements, which are in blue, sit on 3 points. And we'll see that from underneath. Those 3 points are like a 3-legged stool. Why 3? Well, we all know that 2 points define a line and 3 nonlinear points define a plane. So if we push this curved element, or set these curved elements on 3 points, as that bridge goes up and down and flexes, you will, each one of those wings, those blue sections, will always be in a plane. Now, if we attach the rails directly to those, then those rails would move apart and get closer together. And that wouldn't work very well. So we've set those rails on top of, if they moved apart, got closer together, the train would derail or come off the tracks. So we set those rails on what we call bearer bars or ties that sit in each wing. Play this video again. As you can see, is this is this bridges that accordion joint that connects the fixed bridge to the moving bridge. So as that bridge moves up and down, the floating portion, this rail flexes to that position and keeps the, allows that transition, a point transition, to about a 40-foot section. I think here, I'm going to play a video showing some of the, now I'm going to ask someone to speak up. Are they hearing the text, the version of this?
Negative here.
To go and screenshot.
Okay. So yeah, I don't think the, so what you see here are those 3 motions of the bridges. Those are those expansion joints there. So it twists back and forth. So I'll play it back there a little bit more.
What if you go into screen show mode?
You know, I don't think the audio comes across on WebEx with these videos is a problem.
Okay.
So again, backing back up here. What you have here is there's a floating bridge on the Lake Washington. And there's 6 different ranges of motions. The lake goes up and down as the temperature expands and contracts that bridge, and as the wind twists it from left to right, or the loads on the traffic twist that bridge from left to right. So we put these 3 points which each of those wings sit on, and then we put bearings on top of that and connect the bearer bars across and the rails on top. So as the lake goes up and down, we take that point movement and we turn it into a vertical curve up and a vertical curve down. So we went to Jesse Engineering Tacoma, built 2 of these prototypes, and then brought them to Pueblo, Colorado, where there's a 50 square mile test facility for rail. And we built a mile-long track and mimicked the lake movements. Put 500 channels of testing on both the train and the track to understand what was going on each one of those. So we put a lot of forethought and effort into this. We shipped 2 of our cars halfway across country to run on that. So these are actually the Sound Transit vehicles in Colorado running on these. Before we even built it out there to test it out. And what we found with all that testing was that at the design speed of 55, it actually worked pretty well. It had a smooth, comfortable ride. So it was great to check back in with that and make sure that everything is working well. And then here's just some of those pictures from Pueblo where we were working on, where we had built that track bridge. Clearly this was a lake during the end of the last ice age, but now it's just a huge flat plain. So we would jack the rails into the different positions as if the lake had moved. And while the lake goes up and down, it moves about 2 feet from high to low, from the late winter at the low to the spring at the high, and then all summer long it slowly drains down. So the motions are very slow. But we proved all these different motions. We tested it out. And I think the big point here is that what we used on these components were, it's a new and innovative, never done before. Most of these elements are off-the-shelf things. You know, the ties that connect the rail, that's a system that's used today. Underneath the bridge, what we set these things on, they were bridge bearings that you see at the seats of where a bridge have expansion joints. Where the rails, the bearer bars connect to the wings. We use what are called double pendulum bearings. Again, those were developed in California, and they're used on bridge technology. Never used in this situation, but we took that technology and used it here. So we try to take off-the-shelf components, arrange them in a different way, and then apply it to this. And we took what was like theoretically in the computer over 70 KSI stress in rail that can only handle 60 KSI before it snaps, and brought it down to about 3 KSI of stress in those rails from these movements. So well within the working range of that system. And we did it by a lot of advanced planning. We did computer models first, of course, to simulate this. We then did a full-size component mock-up and brought that to the University of Washington Structural Lab and tested components there. We didn't actually learn what we were expecting to learn there, but we did learn how to put it together a lot better. It's just too small a facility. So our next step was to build these 2 full-size bridges, which we did down at Jesse Engineering in Tacoma, and shipped those to Colorado and tested them there. Again, those are the photographs. And I guess the big takeaway on this is, granted, no one else is probably looking, since this is the first time in the world anyone's put light rail on a floating bridge. Not likely a lot of other people are doing this in the future. But the takeaway was define the solution. We had a lot of folks that wanted to, define the problem. We had a lot of people who wanted to define the solution, jump to that next point. But we really stressed defining the problem, going through that problem systematically, defining failure, what worked and what didn't, to sufficiently get us there. There are some smart people who really wanted to jump to some other ideas, like, well, this is the right thing. There's some concepts called 3 beams that have been used on suspension bridges, but those only have 4 degrees of motion versus our 6. Before going there and trying to retrofit that, it's like we really had to step the team back and make sure they were looking at what's unique, what are we doing here, and that really helped streamline this. Also, again, as I mentioned earlier, off-the-shelf components. What are those things that we know how they perform, what they do? How do we incorporate those known type of items into this product so everything isn't new? What we're doing has never been done before, but let's not make it super complicated by making everything new. The more we can use proven products, the more those things don't have to be tested, and we can test the system rather than each individual item. And then, of course, we refined these projects as we went through this process. We learned from each one of these steps, where it is in the computer model, once we went to the testing lab at the University of Washington, and then we did the full size. And of course, at the end, I'm an engineer, so, it's having fun. It's engineering. There's a lot of challenges. It was really hard, but it was really fun to just try to figure out new things, really try to listen to people, use that diversity of the team. We had people from England, from Germany, a lot of people who live in this country but came from all parts of the world that really worked on this. They all approached it a little differently, and that was really fun and challenging. How do we make sure we're listening to each other, hearing each other, taking that time to use the full team? Because that's the only way we're going to get this done, and that's how we did do it. And so, again, it was fun, it was innovative, it's challenging, and in 2023 we'll be running light rail trains across that bridge. The tracks are installed on there. We haven't yet dragged trains across it, but that's coming in 2022. We'll test trains across that and then start running in 2023. There are also other challenges on this bridge, not to think that just that expansion joint was it. One of it was the lifespan of this bridge. As was mentioned earlier, there have been a number of floating bridges that have had challenges. These are the longest floating bridges on Lake Washington anywhere in the world, and they're serving interstates and 6-lane highways. So they're large bridges. This one on I-90 is a mile-long floating bridge. So we're doing a major investment putting light rail on this. So we wanted to make sure that we had a good lifespan of this bridge. In investigating it, we realized that the way this bridge was constructed was great. It had to fit through the locks that connect Lake Washington to the saltwater in Puget Sound. So this mile-long bridge consists of approximately 400-foot wide long pontoons that would fit through those locks and come into the lake. Then each of those pontoons were bolted together, and a bridge deck with cantilevered sections on either side were hung off this to make the final road surfaces. Each one of those pontoons consists of 5 sails wide and 10 sails long, and it's essentially like a submarine inside of each one of those cells. So each one of them is individually watertight to make sure in case something were to happen and get a crack, a leak, it's very contained in that. But each one of these pontoons was just bolted together. What we decided to do was post-tension this bridge 20 years after it was built and do a mile-long post-tension. As far as we know, it's the longest post-tension ever done in the world, and it was retrofitted into this bridge. So that took a lot of engineering analysis. Inside these pontoons, we had to put in reaction frames to jack these cables against and do the post-tensioning. So again, we went to Jesse Engineering in Tacoma. They built up these jacking frames that would hold those cables that we'd eventually jack against. But they had to be installed into this bridge. I remember I was saying earlier, these things, there's 5 cells wide, 10 cells long, and each one of these 400-foot segments that's in total a mile long. We had to break that jacking frame down into small pieces, lower it through a hatchway in the bridge, which is a maintenance access. And then where I said it's like a submarine, there are marine doors between each one of these pontoons that we had to move each of these pieces out to the end of the bridge and then install them. And once they got into that end pontoon, they had to be within 1/16 of an inch where they met up against the concrete surfaces, because we were going to be jacking them with a lot of pressure against that. So again, we used LIDAR, which is a surveying technique to understand where all that bridge works, mocked that all up, measured it, and then brought all these pieces in one at a time. And then here's just some more pictures of where we brought that jacking frame in on the right, poured a concrete blister up against that. And on the left, we're kind of looking down where those cables are going to come out of those holes. This is one of the 5 pontoons on either end of the bridge that we were going to pull and jack this from. In the end, after we post-tensioned that bridge, we shortened the length of that bridge by 4 inches. So think of concrete as not very compressible, but in a mile, we put that much force into that. What this did is greatly increase the strength of this bridge and made it act as one continuous unit, much as the way that a lot of bridges are post-tensioned. So that alone, we think, added a lot of strength and brought up the design life of this bridge, so it'll be serviceable for many, many more years once the light rail begins on this project. Other challenges on crossing the bridge was stray current. Our light rail system operates with an overhead catenary system, and the rails themselves are the return current. So that means that we have electrified current running across those rails. We have to make sure stray current doesn't come off those rails, get into the bridge, and then start a corrosion process on that bridge. Again, it's a marine vessel. It sits in water. While it's fresh water, it's a very conductive medium. And getting stray current into the rebar of that bridge would accelerate the corrosion of that bridge and obviously greatly shorten its lifetime. We also have to attach that those tracks to the bridge. Our normal system of how we attach to an elevated bridge would have required somewhere around 18,000 holes drilled into an existing bridge deck that was post-tension longitudinally. While we post-tensioned the length of the bridge deck side to side was already post-tension. So we couldn't really risk harming any of those penetrations. And then finally, we have the weight and balance. This is a marine vessel. We can't lower it too much in the water or twist it from one side to the other. So on the stray current, we went with belt suspenders, and I like to say belt suspenders and someone else helping hold up your pants. So you see the rail on the top there. We have a clip beneath there with a high isolation fastener, or basically an isolator. Underneath that, we used a high isolation material for a drip edge. So any water that would fall on the rail would then come to this cap and it would flow off the side. So any electrical current that might come off in a rainstorm wouldn't have a continuous path to the deck, because the drip patterns would keep that water from being continuous. Underneath that cap, we put a steel band around our concrete plinth to pick up any stray current that might be on the surface of that block. And then what you see there is a little a nub coming out. We connected each one of these stray currents with a wire, one to the next, and brought all those connectivity points off the bridge. So any stray current that got into that band would get picked up by this wire taken off the bridge before it could get into the bridge deck. And then on top of that, we did a high polymer coating on top of the bridge deck around the rail. So if even some more current got down there, it couldn't penetrate through that. So again, belts, suspenders. We wanted to make sure that we did nothing to harm this bridge and everything to preserve its life. It's a huge investment that the national government made in the interstate system, that the local taxpayers made by their match and by them voting for light rail as well. So how did we attach to this bridge? We said we didn't want to put 18,000 holes in there. Well, we did, first of all, we took the plinths. The design on those was a very lightweight concrete. So we used almost a pumice in those because we didn't want to add too much weight to this bridge deck. Then after we poured those, underneath it, we poured a material called Cork-Elast, which is sort of a spongy epoxy, if you will, that helps absorb vibration. And then those bricks, those blocks were brought out and poured, jacked up on the rails, and we poured a two-part epoxy underneath them to basically glue these down to the bridge deck. Now, we're not just gluing and hoping it works. Again, here we did a lot of testing. We looked at some materials that have been used in Europe for similar but different purposes. We took those to the University of Washington lab. We pushed them, we pulled them to make sure that they didn't stick to the deck so much that they'd rip the deck off for some reason if they were pulled too hard. They failed in the material themselves, so again, we wouldn't damage the deck of the bridge. We also sent a few of these blocks to Chicago and did accelerated environmental testing. So we did heat thaw cycles on these things in an oven freezer sort of element to just see how they lasted long term. Again, a lot of testing, a lot of thinking about that, how these all work together to make sure the long-term durability. And then here you can see that completed system where we've got that polymer on the deck. We've got these blocks that we've connected. Rather than normal railroad ties, where you'd have a continuous block across. Since weight was a big issue on this bridge, we didn't want to load too much weight. We connect each one of those blocks with a steel rod, being a lot less expensive. And then each one of those rods also has an isolation between them so we don't pass currents between those two rails. And then that third rail you see on there is what in the train industry we call a guardrail. So in the highly unlikely event that a train were to derail on a tangent section, that rail keeps the train from going off the tracks too far, and in this case off the tracks and into the lake. Obviously not something we want to have happen. So this guardrail catches it. That's an industry standard used by freight railroad companies. You'll see that a lot of places on railroad bridges, making sure they don't have any derailments there. Another big concern on this bridge is wind and wave. Picture on the left from the 70s, a big storm. We actually had a large storm sink one of these bridges when it was under construction. I will emphasize it sunk while under construction, so it had many issues going on at that point. But we wanted to look at, how much stress is going into this? How much stress are we adding to this bridge based on the light rail? This bridge was built under different engineering codes at the time, bridge codes. They're not seismic codes because there's no seismic activity on the lake, but wind and wave are one of the big drivers. So we wanted to reevaluate all that and see how much effort was coming into the bridge. We also knew that in a huge storm, the State Patrol will sometimes stop operations on the bridge. So we want to understand environmentally, when we get a big storm like that, are we adding more stress to this bridge? And do we need to start removing automobile traffic or light rail traffic to take some of the structural load off that bridge, since that structural load is being eaten up by the in a major storm event? So we had to do a big study on the wind and waves, where they're coming from, what's the fetch on this. So we had marine engineers involved in this project, climatologists looking at where these storms come from. We actually learned that while the design was a storm from the south, which is where most of the large storms come from in the Seattle area, we do get some freak storms that come from the north, and the fetch, or the distance that the lake has to build up waves, is much greater to the north than it is from the south. So that became the design storm, which was different than when this bridge was built. They had assumed the storm is out of the south. So that was, again, part of that reason we wanted to post-tension the bridge and then understand at what point maybe we wanted to start mitigating the loads on this bridge by reducing the traffic. And what we learned is that the average wind speed, about 25 miles an hour, happens, really has no impact on what we're doing. But when we get to about 30 miles an hour, what we've decided, 30 miles an hour sustained wind. So these aren't wind gusts, but this is a sustained wind over a period of time. And I'll get into how we measured that. That what we'd probably do is mitigate by only single tracking, put one train across this bridge at a time, making sure that we have a system to only allow one train on the bridge. And that takes a lot of the load, because the design is 2 trains on that bridge right next to each other with a full lane of four full lanes of traffic on the other side. So a fairly loaded up bridge. So by making sure one train is not there, really lightens the load. How does that impact our customers? Well, it takes a little over a minute for the train to go across this bridge. And we have 6-minute headways or 8-minute headways when we open, probably 6 in the future. So really there'd only be every 3 minutes a train crossing. So theoretically, only allowing one train on the bridge at a time shouldn't impact our service. But sometimes, just the way the service runs, you might have 2 trains out there. So probably relatively little impact. And the chances of that happening when we get to this 30-mile-an-hour wind, it's about once every 5 years is our expectation where we'd have that sort of a storm. Once we get to about a 40-mile-an-hour wind speed sustained, that's when we would probably need to cease operations until the winds died back down, and making sure we weren't stressing the bridge out. Again, this isn't bringing the bridge to failure. This is just making sure it still stays way below its design load. The load it's designed to operate under with no problems at all. At that 40 miles an hour, that's about once a decade we expect to see that sort of a storm. So, it's like a major snowstorm or something else. While that does impact our customers substantially, that's something we can probably explain to them, that we're having a major snowstorm or a major windstorm, that these are disruptions. And at that sort of a storm, you would tend to see a lot of power outages around the sound. It's an explainable event. And again, the most important thing is making sure this bridge survives. And then WSDOT also has the ability to then take traffic off at about that speed too. Generally, they tend to take traffic off because when the winds get that high, cars start swerving between lanes, and it becomes not so much as a bridge structural load, but more of a traffic safety load for drivers not staying in their lanes. And that also then would greatly reduce the stress. And then once the winds drop below 40 miles an hour, we start the operations again. But we had to figure out, really we're basing this on wind, but what we care about are waves. If you think about it, you're out in the environment, you get hit by wind, it kind of knocks you around. If you've ever gone into, knee deep, wading into an ocean and a wave hits you, it'll take you off your feet. And that's just a small wave. So really what we care about are waves. So we had to figure out how to translate wind and direction into a wave height that actually adds structural load. So, and here's a case where we partnered with, instead of world-class scientists, we partnered with college students doing their senior projects, who came to us and said, what do you have? What can we do? What can we work on? And we talked about this. They found these buoys that do wind. They're solar buoys we put out in the water. And for a year and a half, they monitored the different wind, the waves, how those correlated, because this also had an accelerometer on it to tell how high and the waves were. So then we could then correlate wind direction, wind speed, length of time, and when waves build up, so that eventually we can just measure the wind and the direction, put that into an algorithm that tells us what the waves are, and where we have to have a problem. Because if we have 40-mile-an-hour wind, but it's going east-west and not building up waves, we really don't have a problem. So again, it's we reached out, we used the community. In this case, we used a lot of students that had a lot of enthusiasm, spent a lot of time, researching on the internet, doing different things, putting these things out there. It was a great project, and we learned a lot. Clearly, it took some of Sound Transit staff time to work with them, but I think it really helped develop a lot of our young engineers, which is so important. And these are just some of the monitoring and the waves and what came out of it, the data that they came out. So essentially, it was a project from top to bottom we had to think about. We had to come up with, we had 23 different critical items that we were that independent review board talked about, that WashDOT and the feds, Washington State Department of Transportation and the Federal Highway Administration said, until you answer those 23 questions, you can't put light rail on this bridge. And that was great. It was an independent group. It was arduous to go through, but it was important. It gave that independence that they looked at it, they set up a lot of things, and we actually found a lot of other things since then, or going through their issues, to really make sure that we thought about each one of these questions. We took a lot of time. This is a critical piece of infrastructure, today as just an interstate, but in the future as it connects transportation. And the takeaway I'd really like to put is using that community, using the young engineers of tomorrow, using those knowledgeable engineers from all over the world, all over the country, but listening to them, understanding what they're saying, taking that time to make sure that people could question you, and that you were open to those conversations. It's sometimes really hard to be challenged. We had some people who were adamant that the 3-beam was a great system, worked all these places, and we should respect those people who do it and just go with that system. And it is a great system for what it's designed for on 6 degrees or 4 degrees of motion. We had 6. And so some of those tough conversations were good to have and important to have. And I think we came up with a great system that's going to work. And with that, I will conclude and go to questions.
Okay, my first comment is thank you very much for this very detailed explanation. I now have confidence I can drive across the bridge when the train is on the bridge. But I do have a question.
Yes.
You mentioned the wind creating waves, and you talked about this fetch distance and whatnot. What kind of wind does it take to blow over one of these trains?
So it's not blowing over the trains. It's the wind build up waves. The waves strike the bridge, and the bridge is a very long beam, so it bends that beam. So some of the motions each end of the bridge is anchored out there, so it drifts a little north and south. It's not rigidly held there, as the wind blows from the north and the south. But as it blows stronger and stronger, of course, it just goes across against one side of those. It'll move, if the wind's coming from the north, it'll move to the south. But as the wind builds up, more and more of these waves hit it, and it's like, striking the beam, just one wave after another. So it just adds load, sideways load to the bridge. So you have this bending beam action. You then get torsional load from the vehicles, light rail and automobile vehicles going on it. And you get twists as those loads move because you might get heavy trucks for a while, then the trucks leave, there may be a gap in traffic, so the bridge moves back up. So it's constantly moving, very slowly, but it is moving. So it's all
That's my
about
question.
structural loads on the bridge.
I guess my question is more oriented towards the rail car manufacturer. That whole broad side of that rail car can act as a sail sometimes if you get a large gust hitting it.
Right.
So I was just
Right.
curious whether you even looked at that.
We actually did. So when we did a lot of our testing out at TTCI in Colorado, they do not only a light rail, they do commuter rail, heavy rail, a lot of work. So we actually took our car there and put it on accelerometers, tested all the suspension and everything else. So we understood this car very well. The wind on these cars, they're designed for that. And I'll say that only in the sense that we have these trains, as do many places around the country, on elevated guideways that get big storms. They are designed for much more than 40 miles an hour. It's not going to blow them over. They're pretty heavy, but most of that weight, a lot of that weight's at the low end of that car, so they have a fairly good low center of gravity. And of course, the more loaded they are with people, the even better they are with that. But sail area for blowing these trains over, unless you're, literally hurricane sort of winds where we would stop operations, a 40-mile-an-hour wind is not going to blow them off the tracks.
Thank you.
I have a question about maintainability. Are you using any internet connected sensors to help you understand the movement and changes of the bridge and perhaps when it needs to be maintained? Obviously, technology can help with maintenance needs rather than having a person go inspect it all the time.
Right. So some of the answers are yes. We have anemometers, wind gauges, all that on the bridge constantly. So that's always monitored. We have backup systems. This bridge is maintained by WashDOT. Inside the pontoons, they have all sorts of gauges on, in case there's water leaks, water intrusion. They have automatic pumps, but they also, those are connected to them. We did look at sensors showing the movement of the track bridge. But really, since we put it out there, and that was our early design plan to monitor that track bridge. How's it moving? Is it within parameters? We know from lake levels and what's going on where those should be. So we decided we probably had a lot more issues with trying to monitor that and getting the right gauge in there and getting false negatives and shutting down the system on something that really moves quite slowly. We know when the lake level is dropping, and it drops, like I said, 2 feet over 6 months. So it's a pretty low course. And then we do track inspections on all of our tracks at least once a week. Probably be doing it more often on here. So that's something that during those track inspections where we walk our track, when I say track inspections, we literally walk every foot of our track weekly to look for, broken rails, although there's other ways of determining those, but any loose clamps, those type of things, maintainability, because these are critical systems. And one of their inspections will be looking at those track bridge and making sure that all those components are where we expect them to be given the existing lake level. And we just found that since we're out there anyway and walking that weekly, if not more often on these, that human interaction of really seeing it rather than relying on that video camera on a target or something else, we found it to be more reliable. Now, would you want to send people out there if we didn't have to be anyway? We probably would have worked a lot more in the internet connections. But since we're out there weekly and it's a very slow movement, we figured that was a better way to go.
Gotcha. Is there an estimated lifespan for this design?
I think the lifespan of the tracks is going to probably exceed the lifespan of the bridge. What is the lifespan of that bridge? I mean, we hope it'll last 100 years, but clearly we've done a lot to strengthen that bridge, make sure the straight currents come out. Oh, I'll say another thing. There's also an impressed current that goes into this bridge. So in the unlikely event that we even get some stray current on the bridge, or it shows up from something else, they have lighting systems and other things on the bridge. There's an automatic stray current impression system that also helps. So that's something that is automatic, that's monitored. But it's a piece of infrastructure that has already, before we got there with light rail, a lot of maintenance on it, a lot of eyes, and they're looking at it constantly because it is pretty unique. It's again, it's a marine vessel that they need to trim it as the lake goes up and down. They lengthen and shorten those anchor cables. So those are all things that they're constantly looking at, checking, making sure debris isn't getting washed up against that bridge and getting that out of there. So it is a maintenance intensive piece, and we decided to build on those folks that are already out there to make sure that they're also trained in this stuff.
Someone had texted in the question about seismic retrofitting.
Right. So the floating bridge itself does not experience seismic. It's not a seismic design structure. It's dampened by the lake. Now you can get a bathtub effect, which is different than seismic. So the bridge itself, no. We did post-tension it, but that was to basically bring it up to strength when we figured out the new wind and wave analysis combined with our new light rail. Besides adding the light rail, the three main lines of what used to be westbound Interstate I-90, we made into 4 lanes. We added an HOV lane to it. So we added some traffic loads. So and then we added the current design criteria for those loads onto this bridge and decided we needed to strengthen it. So we strengthened the bridge for that. Now the approaches to the bridge, which are sort of standard, bridge on, as you come out of the tunnels in the Mount Baker tunnel on one end and the Mercer Island tunnels on the other, you go onto some elevated bridge structures. Those are more of a standard structure. And yes, we retrofitted those to current earthquake standards on the approaches to the bridge.
The post-tensioning cables, that's a huge, I would think, extra static load on the bridge. Am I incorrect in assuming that, or is that?
Yes, we added a lot of load to this bridge. The rails weighed a lot. The plinths themselves, even though we used lightweight concrete and tried to make those as small as possible, they of course add a lot of weight. The trains, when they go across, we designed them for our crush load, which is called AW3, which is like over 200 people on each car. So we assumed every car going both directions is completely loaded full of people. We loaded up the sidewalks next to it. So yeah, we added a lot of load to this bridge, and look for that worst case scenario. But yeah, it is a lot of load. And then, so that was sinking the bridge. Obviously it lowers it slightly when you add that much weight, but the bridge were built with ballast, like a lot of other ships. In this case, it had gravel in the bottom of those pontoons. So part of the whole effort of this was per pontoon, not for the whole bridge, but per pontoon, we wanted to make sure the weight and balance was done as we added the rails to one side, traffic to the other, pedestrian loads, of course, the cables to the whole bridge. We mitigated some of that by removing the outside concrete rail. It was a traffic barrier rail that doesn't really do much for a light rail vehicle. The way you guard a light rail vehicle is that guardrail that I showed in that photograph, that third rail. That's how you keep them from derailing and going anywhere. So those are some of the things we did to mitigate the weight that we added to that. We did, I think, lose an inch of freeboard on this bridge, but that was all within the design parameters that this bridge could accept, and keeps the anchor cables that come out of the bridge well above the water level. So the anchor cables come out of the interior pontoons of that bridge and actually go out to the sides. But yeah, that was part of a lot of the design. How do we do that? Normal light rail is what's called 115 rail, which means it's 115 pounds per 3 feet in length. These historic standards, I'm not sure where they came from. On the floating bridge section, we transitioned, for instance, to 100-pound rail. plenty fine for a light rail. The 125 is what's used for freight rail. It's generally acceptable. The 100 rail is an older system. I had to kind of look around to find those older rails, but that saved a bunch of weight. So we look for all these mitigation strategies on weight and balance to try to figure out the best way to keep that structure as light as possible. Again, I showed some of those concrete plinths weren't all the way across. We did a plinth on either side that we glued down, and we put a steel bar between them. That's a lot lighter than the concrete. And we went around and around and around on those questions. Yes.
I'm sorry. On that note, this project, as well as honestly any project in the real world, is one of compromise. So you had weight restrictions, you had budget restrictions, you had timing restrictions. If you had like a genie in a bottle and you could have had one thing that you had to give up, what would it be?
Good question. Never safety. So that's always there. I think one of them was, as we looked at the track bridge, we were willing to give up some of our design speed across that bridge. Fortunately, we didn't have to. I think in storms, we've been willing to single track. That's an operational nightmare to suddenly decide we have to do that. We have to put all those signal systems in. So that was, a compromise, but it's for the structural integrity of the bridge. And clearly in large storms, not because the train will blow over, but just because there's so much load onto that bridge, we decided that the most prudent thing to do was to pull the trains off. And again, those design loads were about half of the ultimate stress of the bridge. So clearly below, the breaking point of the bridge. What we wanted to do is stay within the working stresses of the bridge. So something that you can cycle through and it doesn't really wear out the bridge, doesn't accelerate the wear. So I think that was some of it. I talked a little bit about the maintenance. We're going to do a lot of walks on this. So it's going to take, that's another compromise. We have to have people walk and look at it. But I think this just warrants that extra look. I think there were people on other places that didn't want to give up the center lanes, right? They wanted to use that for automobile traffic. I think that was a compromise that the region had to make. The voters voted for that, and this was the project. But so we did things like put that fourth lane in for HOV. That narrowed up some of the shoulders on the floating bridge. So those are some compromises. They're kind of making all over the place. Never on safety. Hopefully never on the durability of this. And the others cost. This costs money. It costs a fair amount of investment to look at this program early. We started really early on it. We dug into it early. Our board, trusted the staff to give us some money to go out and look at this, to build a mile of track in Colorado and ship 2 trains there and spend months testing it. That we could have saved millions of dollars on that. We probably could have argued that we didn't have to post tension the bridge. We could have said, let's just look at the bridge and the old design criteria rather than the new modern weights on this. But we chose to, add that post tension after we looked at the more modern criteria that the bridge was not built under, but bringing it up to some of those standards. So those are, some of it's cost, but always with the mind of safety and our customer involved. And some of our customers, quite honestly, besides our passenger, is WashDOT that runs and maintains that bridge. It's the FTA who funded 90% of that bridge, and it's part of an interstate system. It's making sure they're on board. And that's not always easy for people that have a lot of other things that they're doing and have to check in on this and are being asked by Washington to make sure, Washington, D.C., that we're not compromising the bridge. So that took a lot of time and effort and hand-holding to make sure they understood what we were doing, that they trusted what we were doing, that we were demonstrating that we're being really open, and that we were telling them when we were having problems, when we were seeing concerns. Not crying wolf, but not waiting until it was so obvious that we couldn't hide it. It's choosing when to say, yeah, here's some of our challenges. Here's things we need to go in. I can't tell you the number of hours of meetings with the structural engineers at WashDOT to, you know, and they were our biggest critics, as thank goodness they were. You know, your critics hold your feet to the fire, and that's good. It keeps you honest. It can make it fun, challenging. So those are all those compromises, is taking that time on this one, recognizing early, and not just saying, you know, if we started late or we're under a time crunch, that's good enough. Let's just keep moving. Because I think we've all seen examples in many industries where that rush, the backside of that comes around and hits you pretty hard in the back of the head. There's times you just have to say, no, we got it wrong right now, and we need to go back and try something else. When we first took it to the University of Washington, the structural lab, we expected to learn a lot. We learned things we didn't expect to. We couldn't prove what we wanted to. So we had to redesign that test and realize, you know, we need these full-size mock-ups and bring them to Colorado to do it. That was good knowledge. It's a disappointment we didn't learn what we wanted to there, but then we said, okay, how do we get that? How do we get to where we're comfortable? So time, money sometimes.
So I kind of concluding from your discussion here that this bridge was not originally designed to accommodate rail traffic. Is that true?
Yes and no. It was, when it was built, the center lanes were, if you look at the original documents that FHWA put together, it was built under the center lanes were designed for high capacity transit with an interim use of HOV lanes, or at that time they were called carpool lanes. So that was its design. Did they dig into what the light rail, how it was attached, and all these other items? No. So it was designated to do that. But like many structures, codes evolve over time. And usually in this region with seismic, they tend to increase. The highway design loads, a lot of the trucks have gotten, you know, they used to run 60 PSI tires. They're now running, what, 120. So the loads are a lot heavier that these trucks are carrying and bigger. So there's a lot of criteria that has changed since the bridge was built. And we applied that criteria to an older bridge and then figured out how to make it work. And that's where eventually is coming up with post-tensioning. We did look at some really innovative stuff. We looked at, for weight, if we could use fiber carbon cables to save a whole bunch of weight. The traditional cables you use, not only do you have to, they're steel and heavy, but then you put them in conduits that you need to environmentally seal so they don't rust. And you do that by basically pumping them full of a grout or concrete, which is a lot of weight. But the carbon fiber technology just wasn't quite there yet. So we backed out of that and found other ways to weight mitigate. It would have been great if it was, but we just couldn't figure out how to actually jack a mile-long carbon fiber. Because when you grab onto carbon fiber, you can crimp it and cause damage. So those were some of the different, you know, just sort of dead ends that we hit, and we had to back out and say, okay, we thought we had a weight mitigation strategy that wasn't working, and that's where we eventually came up with this. I think I said an inch, but it's really a half-inch freeboard that we lost. But to answer your question, yes, it was designated for high capacity transit, undefined what that was at the time, but not specifically designed for a light rail.
Thank you.
So I just have it's more of a non-technical question, but I mean, was the decision to make this floating versus, let's say, a conventional bridge, was that just because the floating bridge was already there for the roadway and the light rail was just added?
Yes, so the floating bridge is existing. Like I said, when it was built with the idea of high capacity transit across the lake someday being added to that. And that's a whole environmental process we went through, and eventually the voters of this region voted for light rail to go, to be that high capacity transit. But the reason it's a floating bridge is because the lake's so deep. Structurally, there's just no other way to really.
Oh, that was just my next question. I mean, it sounds like with all the technical challenges and whatever has been done, it seemed like that was truly a more expensive concept versus a regular bridge. But it was literally the depth of the water which prevented that.
Right. And that's why we have 3 floating bridges across Lake Washington, 2 on I-90, one for eastbound, one for westbound in the light rail, and then one for Highway 520 that connects sort of the North Seattle, University of Washington, out towards North Bellevue and out to Redmond, Microsoft, that area.
Okay.
And the reason they've chosen floating bridges is because the depth of the water and I think it's well over 400 feet deep in the middle of the lake, just to the muck that's down there.
So it must be deeper than something like San Francisco Bay or so, because that bridge there, the famous one, I mean, that's a solid bridge, right? And it goes all across that bay.
The Bay Bridge? Yes.
Yeah. Oh, I wouldn't have thought that. That's interesting.
The Puget Sound was, in this area, was heavily influenced by the last ice age. The glaciers coming out of Canada came down through here. So there was well over a mile of ice on top of where we currently are. And that meant not only was it a mile high, it was quite deep in different places. And the main spine of Seattle between Lake Washington and the Puget Sound is basically lateral moraines from those retreating glaciers, where they left a big mound of rubble, if you will, between a couple of fingers of glaciers that came down. One being much larger, that was the Puget Sound, and the other one being Lake Washington. And then there was another one to the east that kind of dug out Lake Sammamish. But those were kind of north-south glaciers, and their lateral moraines were what kind of formed the hills up behind Seattle.
Just a quick one, I think, then we'll probably wrap it up. Now, basically, a train, when you lay train tracks, they're always subject to temperature changes and
Yes.
overall environments. So I'm assuming, I'm not a train expert, I'm coming from aerospace, but so there should be some level of a tolerance which that wheelbase can accommodate if those tracks go away. Now, at the beginning, you showed this impressive video. So most of this motion is basically being adopted by this construction and the movable passes. Is there still something which may still come through to the actual train track in terms of variations, and how much do you think that would be?
Great question. I didn't touch on that. There are so many issues on here, but yes, rail movement is another big one. On our normal systems, what we have continuously welded rail. There used to be bolted rail back during the I'll say steam engine time, even into the early diesel locomotive time. And that's that clickety clack of the rails where those joints happen. And those bolted rails allowed for the expansion. With continuously welded rail that we have on all of our major freight systems today, at every clamp where the rails clamp to a tie, which is about 30 to 36 inches, depending on the system, you have about 3,500 pounds of downward holding force. So essentially, you allow that stress to build up between each one of those ties. And if it gets beyond 3,500 pounds, then the rail starts to slip from expansion or contraction. So that's how we handle it on all of our elevated structures. That's how train tracks, even with ballast, hold that all together. On the floating bridge, because we've glued these plinths down, that 3,500 pounds from each of those clamps, excuse me, and there's 2 clamps per plinth, would translate into an overturning moment on that plinth. So what we actually have are 0 toe load clips on here. So we allow those rails, even though they're continually welded across that bridge, to expand and contract. And of course, even as that bridge, that track bridge moves up and down, as you go through a curve up and then a curve down, that length, minusculely, but it will change. And we accommodated that expansion rather than clamping it at each rail like we do in the rest of our system. We allowed it to run off the bridge to what are called in industry Conley joints, or think of a mitered joint. Again, that's off-the-shelf technology that's in the rail industry. It's been used for ages. They oftentimes use it on sharp curves, just beyond that, where you don't want, you can't hold all that expansion and contraction in a sharp curve because you just push the curve out with all that force. So they allow that rail to slip into these Conley joints or a mitered joint. So we took all that expansion and contraction off the bridge, so we weren't putting those forces into the bridge deck. Again, that was a great insight in seeing that, and that was one of our challenges in how to do that. And then at that Conley joint, that accepts the expansion and contraction, and then beyond that, we have our standard rails that we clamp down for continuously welded rail.
Oh, all right. Thank you.
Well, this has been a fascinating feather in your career cap, no doubt.
It's been wonderful. I've often said I'm luckier than I am smart, and I got lucky to be on a job with a lot of really smart people. So it's been wonderful.
That's great. Is there an engineering challenge you'd love to take on in the future?
Wow, that's a good question. You know, this one was pretty monumental. It had so many things, and I didn't realize what I was getting into. But every day I just enjoy. There's a lot of little stuff that seems mundane, but you got to get it right. And I'm taking a lot of this knowledge right now, later in my career, in my 60s now, and into working the early planning processes. A lot of the things we're working on to make sure early in the process that the planners and the people that are, their main job is really going out and talking to the people and making sure we're getting it right with the community. Because we've all seen examples of engineers building really great engineering products that the public goes, what the heck? So we have a whole group of people that are really good at talking to the community and making sure we're hearing them and listening to them and getting the right system built that serves their eventual needs. But being there at that early stage to also say, and here's the engineering needs, and making sure we're getting into it. And that's actually really fun because it's, it's taking, knowing the detailed issues and then bringing it up to a big picture to make sure that early in the process, we haven't, backed ourselves into a corner that we have to now do something Herculean like this. And nothing against the people that designed this floating bridge. They didn't know what they're getting into, but they sort of said, and they'll figure that out in the future. And that was probably the right time to do it. But here, our future isn't that far off on light rail. So, those engineering challenges are really fun too. They don't light up the headlines, but they make it fun to go to work every day. It's not fun to go to work. You need to find another job.
I loved what you said at the beginning, where you had to get really crisp and clear on the problem and not focus on the solution, because that you had many solutions being thrown your way. That's just a really critical part of any problem solving, is to really understand what the problem is. And then you had a very strong customer focus, which I really appreciated.
Yeah. And then redefining that, checking in. Are we still defining the problem the same way? Because sometimes you learn new things. But yes, that is so critical. It's, I guess, in my career, one of the things I've learned and then I'm really trying to pass on is getting away from that. Yeah, it seems really obvious that that's a solution, but just take the time to define the problem and not go backwards. which it's easy to do because there's a lot of really smart people in this industry that's like, I can just see it. Like, you're probably right, but it's like showing your work when you're back in high school. It's like, obviously, you know the answer. You could write it down on a piece of paper, and your math professor would come back and say, show your work. And that's part of what this is. It's that discipline, and it pays huge dividends. It really does.
That's great. Well, are there any more questions? I want to thank you very much for spending time with us and sharing your insights and experience. It was really, really interesting. Thank you.
All right. Well, thank you for inviting me, and
Yeah, thanks,
have a
John.
good holiday season and New Year.
You as
You
well.
too. Thank you.
When the new 14-mile Eastlink light rail opens in 2023, riders will have a brand new option for crossing Lake Washington between the east side and Seattle. With shifting lake levels and weather conditions, the tracks need to accommodate 6 different ranges of motion as they cross from the fixed bridge to the floating portion of I-90. Even though these motions are barely perceptible, it's important to accommodate the transition with a system called a track bridge. Because this is the first time light rail trains will run across a floating bridge anywhere in the world, Sound Transit enlisted world-class engineers to meet the challenge. Here's what they came up with. At this transition, the rails will rest on a series of bearings and plates that allow them to move with the changing lake and bridge conditions. Sound Transit partnered with Jesse Engineering in Tacoma to build 2 full-size track bridges and test them under simulated operating conditions in Pueblo, Colorado, home to the Transportation Technology Center. It was here where light rail vehicles ran hundreds of times over the test track bridges. In this controlled environment, we were able to mimic the forces and movement the track bridge will experience during normal operations. Engineers were able to record more than 500 channels of data during each pass. Among other factors, the test monitored for ride quality and stresses on the track bridges at various train speeds. The track bridges passed all the critical test criteria, and the ride quality on the trains was good at the planned speed of 55 miles per hour. We're confident this technology will ensure a safe and comfortable ride for thousands of people every day when Eastlink opens in 2023. For more information, visit the project site on the web or sign up for the latest construction alerts.